All right, this is part one of our mole unit, and we're dealing with chemical quantities. So you do need to have your note packet, your calculator, and your periodic tables out on your desk for what we're going to do in this unit. All right, so the mole. The mole is one of the 7 base units for the SI system. If you remember, the SI system is really just the metric system. All right. So it measures the amount of a substance, and it's important to realize that mole will be the abbreviation MOL as we go through in this unit. All right. Now, let me move this down here. I think that'll be a better place for it. The form in which a substance exists is known as its representative particles. Now, representative particles are going to be important to understand, and for each type of substance, there's a different type of representative particle. So representative particles can be things like atoms, they can be ions, they can be molecules, they can be formula units, and actually they can just be anything. All right. But representative particles are just a specific way of talking about a substance and its smallest parts. Okay. So just as 1 dozen is 12 representative particles of eggs, a mole is going to be 6.02 times 10 to the 23rd representative particles of atoms, or representative particles of molecules, or representative particles of formula units. So we will use this, and this will be a new conversion factor that we're going to use. So this is a really giant number. As you can see, it's got lots and 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 lots of zeros. So let's talk about it. Again, 1 mole is going to be equal to 6.02 times 10 to the 23rd atoms. Okay, so this is going to be a key part right here. When we're talking about moles of an element, so that's an element, then its representative particles are going to be atoms. Now, when we're talking about a compound, this compound happens to be made of 2 nonmetals. If you look on the periodic table, oxygen is on the right side of the staircase, and hydrogen is not officially included in your alkali metals, so it is considered a nonmetal. So when you put 2 nonmetals together, they create a compound. Okay, so we're going to say this is a compound, because H2O is a compound. And when it's 2 nonmetals, then the representative particles will be molecules. Then if everybody will put their finger on Na, which is sodium, and then you put your finger on Cl, which is chlorine, okay, you'll notice that your fingers are on opposite sides of the staircase. That's because sodium is a metal and chlorine is a nonmetal. All right, so when you have a compound that is a metal plus a nonmetal, you're going to end up with representative particles that are known as formula units. Okay, so that's going to kind of be important to understand, and that, you know, kind of, we can also just say a mole is of something is a mole, is that something. But these 3 are the ones that you really need to be aware of. Okay, these are the atoms, the molecules, and the formula units. That's what you're going to need to really be aware of, and when you use those. So elements will be atoms, 2 nonmetals will be a molecule, and metal and a nonmetal will be formula units. All right, so how much is a mole really? Let's think about that. Okay, well, if we were going to have 6.02 times 10 to the 23rd watermelon seeds, the watermelon that this would be found in would have to be slightly larger than the moon itself. If we had 6.02 times 10 to the 23rd donut holes, like from Shipley's, then we would cover the entire Earth, and it would be 5 miles deep. If we were going to have 6.02 times 10 to the 23rd pennies, then 1, that's a super big, a lot of money, and it would make at least 7 stacks that would reach the moon, okay, of pennies. If we had grains of sand, then it would be more than all the sand that's on Miami Beach. And if we had blood cells, it would be more than the total number of blood cells found in every human on Earth. So that's kind of a big, 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 big number. All right. So we might have this question: how many molecules would be in 3 moles of water? Well, this is going to be a lot like our dimensional analysis questions, and we're going to be looking for molecules, and we're starting off with moles of water. Water happens to be H2O, so I'll use that as its compound. That's why it's a metal and a nonmetal, so that's why we call it molecules. So let me use blue instead. So we're going to say 3 moles, and I abbreviate moles, MOL, of H2O, and I'm going to always put what I'm talking about, okay? And then we're going to say for every 1 mole of H2O, we're going to have 6.02 times 10 to the 23rd. And now for molecules, I'm going to put MC. I'll always do that. It's kind of like when we got meters and miles confused sometimes. I would always use MI for miles, and then I would use just M for meters. So you have to be careful about that. So then in your calculators, since both of those numbers are on top of those factors, we'll multiply them. And we'll do 3, and then we'll do times 6.02, and then you'll use your second comma button, or you'll use your EE button, wherever that might be located on your calculator. But most of the time in class, we use our second comma button, and then we will type in 23. Now, our answer we get in our calculator is 1.806 times 10 to the 24th. First of all, don't put that E on your paper, okay, that shows up in the calculator. Just go ahead and do the times 10 part, all right? So, but we're only allowed 1 significant digit because we started with 1 significant digit. Our 6.02 actually is considered an exact conversion. So since it's an exact conversion, it has an infinite number. So we'll never use 6.02 times 10 to the 23rd as a way to actually figure out our significant digits. So we're only allowed 1 significant digit. So that one, and then we've got to look at the next one. It's going to cause that to round up. So my final answer here should be 2 times 10 to the 23rd, or excuse me, 24th. Let me fix that. The 24th, and this would be molecules of H2O. All right. So let's talk about how to do a bunch of these problems, because this is kind of what we're going to do in this first part here. All right. Before we go too much further, though, we do need to talk a couple of things. We need to talk about some certain elements that are only stable when they're either in pairs or with other elements in a compound. So this is like that friend that you might have that never seems to be able to be by themselves. Like if they go anywhere, they either go with their friend, like their friend set. They'll go like with their best friend, or they seem to be in a couple, and they're always with their significant other, like their boyfriend or girlfriend. Okay, so it's that they're always going to be in a group of some sort. They're always either going to be with somebody just like them, or they're going to be with their in some sort of compound. So these are known as the diatomic elements, and it's important that you realize they're always in pairs or with other elements or with other elements in a compound. So this is the only way they're stable. Now we have 7 elements on the periodic table that are these diatomic elements, and they're hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. A way to remember it would be the memory trick is H. Broncliffe. There is another memory trick though, and the other memory trick that I know is Brinkelhoff. I'm not a big fan of this one, but you know, some people like it. It's still the same 7 elements, but it's just rearranged in a different way to say it. So Brinkelhoff would be another option. And then there's one other option, and it's known as seventh heaven. And the reason why it's known as seventh heaven is because of the fact that oxygen, nitrogen, fluorine, chlorine, iodine, bromine, and iodine all make a 7 on the periodic table if you find those elements. Okay? They make a 7 on the periodic table. And then you have hydrogen over here. So that's your heaven. So seventh heaven. So that's another way to remember it. So if you're more visual, that one might work better for you. But otherwise, H. Broncliffe works great, and it's a really good memory trick. Now, Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. It's the value that I was talking about for representative particles. It's named after Amadeo Avogadro. I'm not actually going to hold you to that, but you will need to know it's Avogadro's number. But he did work in the 1800s, which allowed us to calculate this number and allowed him to. I won't go into all the details about how he actually did that, but he did actually calculate this value, and so he got credit for its name. Now, the mole, like I said, is the chemist's dozen. Um, our mole is 6.02 times 10 to the 23rd. We use it specifically in chemistry to represent things. It's a convenient way for us to count really large numbers of atoms, molecules, ions, all those kind of things. Now, it's kind of like a baker's dozen. Bakers have a specific dozen, and they know it to be 13, and they use it specifically for them. So a mole is kind of our um, specific value as well. So again, it is a new conversion factor. Remember, with a conversion factor, we can work with one number on top or the other number on top, depending on which way we want to rearrange or whatever we want to cancel out. Okay. So how many moles are 1.2 times 10 to the 25th atoms of phosphorus? So we've got moles, and we're starting with atoms of phosphorus. Now, phosphorus is an element, so atoms are a representative particle. Okay, so we're starting off with 1.20 times 10 to the 25th atoms of phosphorus. Phosphorus is the letter P on the periodic table. So I'm then going to want to put atoms on the bottom to cancel out, and then I'll put moles on the top, and that will be moles of phosphorus. Well, I know for every 1 mole, there's 6.02 times 10 to the 23rd. So because that number is on the bottom and 1.2 times 10 to the 25th is on top, when we go to our calculators, we're going to divide. So we'll take 1.2 second comma 25 divided by 6.02 second comma 23, and then we will end up with our number in our calculator that's 19.9336. Well, we're only allowed, according to our first number, to have 3 significant digits because 1 counts, 2 counts, 0 counts because there's a decimal in the number and it's after non-zero digits. So 1, 2, and 3, that number does not cause this one to round up. So we leave it as 19.9 moles of phosphorus. And that would be our answer. Okay. So our next one, how many atoms are in 0.750 moles of zinc? So we start with moles, but we're looking for atoms. Again, zinc is an element, and so atoms is a representative particle. Okay, so we're starting with 0.750 moles of zinc, which by the way is 3 significant digits. So my answer is going to end up with that as many as well. I'm going to want moles on the bottom to cancel out, which will mean I'll have 1, and then I'll have 6.02 times 10 to the 23rd representative particles, which here is going to be atoms of zinc. So since those numbers are on top, we will multiply 0.750 multiplied by 6.02 second comma 23, and we will end up with 4.515 times 10 to the 23rd in our calculator. And it's really important that you actually do these in your calculator because your calculator is going to be your friend later on. So we'll look at that third digit after the decimal because we'll have 1, 2, 3 digits. And that 5 will round that up. So we'll end up with 4.52 times 10 to the 23rd. And this will be atoms of zinc. All right. So now our next one is molecules. We're looking for, and let me change colors real quick because we're looking for molecules if we have 0.40 moles of N2O5. Now N, put your finger on N on your periodic table. Put your finger on O, which is oxygen. Okay, they should both be on the right of the staircase, which makes this two nonmetals. That's why this molecules is being used because this is the representative particles of a compound of two nonmetals. All right, so 0.400 moles of N2O5. Now you won't use those numbers that are in that compound at all right now. You will later, but you don't use them right now. So we're just using what's in front of the unit. So this is just telling me specifically what compound. So moles is going to go on the bottom of N2O5, and that's going to be 1. And then they're going to be represented particles, so 6.02 times 10 to the 23rd. And this will be molecules. So I'm going to write it as MC so I don't get molecules and moles confused of N2O5. So moles and moles cancels out there. We're going to end up multiplying it in our calculator. So 0.4 multiplied 6.02 second comma 23rd. And we get, excuse me, 2.408 times, oh, that's not good times, 10 to the 23rd. Okay, so we can only have, again, 3 significant digits. This one does not count before the decimal. Leading zeros don't count. This one counts, and these zeros count because they're after a non-zero digit, and there's a decimal in the problem. So there's 3 significant digits. So 1, 2, 3. I look at this one, it will round that up, so it'll be 2.41 times 10 to the 23rd, and I will have molecules of N2O5. So again, you're going to want to use MC as your molecules abbreviation for your unit labels. All right. So I have a joke here of what did Avogadro teach students in his math class? Well, multiplication. Okay. So how many moles are contained in 1.2 times 10 to the 24th molecules of CO2. So we used molecules, which are representative particles, because we're talking about CO2. And if you put your finger on carbon and you put your finger on oxygen, they are both on the right side of the staircase. So we start with our 1.20 times 10 to the 24th molecules, MC, of CO2. And so then we're going to want molecules of CO2 on the bottom and moles on the top so we can solve. And we know for every one there's 6.02 times 10 to the 23rd for our conversion factor. Since they're top and bottom, we will divide. So 1.20 divided by 6.02. Second, oop, I did not type that in my calculator right. Hopefully somebody was yelling at me. 1.2 second comma 24 divided by 6.02 second comma 23, which will then give me an answer in my calculator of 1.99336. That's what I get. Okay. Well, I'm only allowed 1, 2, 3. So 1, 2, 3. This one will not cause those to round up. So it'll just be 1.99 moles of CO2. Okay. Hopefully you're getting the hang of it. All right. So your friend gives you a gold ring that contains 2.3 moles of gold. And we want to know how many atoms, that is, because we're talking about gold, which is AU. It has its own square on the periodic table. It's an element. Then our representative particles are atoms. So I'm going to give you a second to go ahead, and I would say go ahead and pause this and see if you could do this one on your own, and then unpause it and check your answer. So hopefully you're able to get 1.4 times 10 to the 24th atoms in your calculator when you round it correctly. So this will actually end our first section of notes, and hopefully you understand how to convert representative particles to moles and moles to representative particles, and you understand the importance of the value of a mole.